Good morning. In today's video lecture, we can see regarding the mechanism of oscillation of two reflex klystron oscillator. Okay, mechanism of oscillation of reflex klystron. So in the last class, we have discussed regarding the how construction of the reflex klystron, which mainly consists of a single cavity and all other things similar to that of two klystron amplifier. But additional thing here we are keeping is nothing but a one Doppler electrode, which is being connected to a negative voltage. So what happens means the electrons that is being generated by the electron gun will be travel towards the Doppler electrode, and it is being repelled by the Doppler electrode because of the negative voltage that is being connected to the Doppler electrode. Okay, so what happens is the electrons will be returned back to into the same direction. So there will be a exchange of energy will be there, so which will lead to the oscillation of what you call that reflex klystron. So this is happening in reflex klystron. So I will just point out some of the things as well as the application diagram of a reflex klystron oscillator, how it works. Okay. So I will write first at some point. Let me come to this. I have just draw the initial case of the application diagram here, but we can come across with this diagram. But I will write some of the points related to the mechanism of oscillation of reflex klystron oscillator. Okay. So let me write the first point. Initially, it is being assumed that the oscillation will start from a noise or a switching transient, and this oscillation are sustained by the device operation. Okay. So the process of sustaining the oscillation can be understood with the help of the diagram we are going to discuss here. Okay. So the first assumption that we have made is that it is assumed that oscillation starts. So initial case we require the oscillation. So that oscillation starts from the noise as when it is being turned on, noise, or by a switching transient okay, and this oscillation are sustained by the device operation. Okay. So the process of sustaining oscillation, write that one. The process of sustaining oscillation can be understood by using the diagram what I had been drawn here. Okay, that is the application diagram. The process of sustaining oscillation can be I can write clearly. Okay, can be clearly understood with the help of what diagram called as application diagram. It is clear to you. Okay. That the what you call that shown in the figure. That figure I will just Just now I will explain to you how it goes. Okay. So second point what I have to discuss is the RF voltage that is produced across the gap, that is produced across the gap by the cavity oscillation. The RF voltage produced across the gap by the cavity oscillation. They act on the voltage, that is the RF voltage that is being produced across the gap by the cavity oscillation will be acting on the electron beam, that is been traveling to cause what type of modulation? To cause velocity modulation. Okay. This thing I have explained the yesterday's class. Okay. The RF voltage that is being produced across the gap by the cavity oscillation acts on the electron beam to cause velocity modulation. Okay. So this is the case. So I will just explain the initial condition. That is, this is the applique diagram. The first the diagram that is indicated here is nothing but the position of the rippler. The second, from here to here, it is nothing but the rippler space as indicated here. The rippler space. I will show the position of the gap. I will draw that one, how the graph is becoming. And this is the signal that is being given across the gap, that is nothing but the voltage across the gap, that is given by Vg. Okay. And below we have written some sort of thing that I will explain while coming to the while drawing the graph. Okay. So I will take this point as the reference. That is the red line. What I have been shown here as the reference point. That is nothing but the electron A. It is indicated with the dotted lines from this voltage gap. Okay, voltage across the gap. So this point is nothing but the reference point where the electron will travel with the initial velocity that is not affected by any other force. So it will move with a velocity equal to that of velocity, initial velocity, that is V0. Okay, so that we can explain it. So in this diagram, I will call this A as the reference electron that passes through the gap when the gap voltage is 0. That's the first point. And now you can see that this graph is going to the negative. Then the gap voltage is 0 and it is going negative. Electron A, this is the electron A. Since the gap voltage is 0, the electron A is unaffected by this 0 voltage across the gap. And it continues to move with the initial velocity V0 till it enters the what you call as the rippler space. You can see that in the figure. Till it enters the rippler space. Above we had drawn that figure. Okay, this figure. So this electron, one of the electron, I call this A, B and C. A, B and C, or early electron, reference electron and late electron. Okay, call like this. EL, early electron, reference electron. What are we called as? Early electron, reference electron. Before something like that you give. Okay. True electron, early electron, reference electron will be moving with the initial velocity V0 till it enters the rippler space. This is nothing but the rippler space. Okay. In the rippler space, what will happen? In the rippler space, there will be a force of repulsion will be that will be act on this electron. And this force of repulsion is mainly due to the negative voltage. You can see that the negative voltage that is being given to the rippler electron. Okay. So what happens? The electron will penetrate. The electron penetrates into a certain depth in the rippler space due to its momentum. Okay, that is shown in this diagram. I will show you here. What happens means this electron, what you call it, the reference electron uh, uh, A, that will continues to move with the initial velocity v naught till it enters into the Rippler space, and in the Rippler space a force of repulsion will be act on electron A due to negative voltage on the Rippler. Okay, so this electron A, this electron A penetrates to a certain depth in the Rippler space. So this is the Rippler space, this graph. Okay, in the Rippler space, penetrate into a certain depth in the Rippler space because of what? Due to momentum. Due to its momentum. Due to its momentum, it penetrates into the Rippler space into a certain depth. That is shown in the figure D. Okay, figure D. This one. Okay, this depth. Okay, so electron then stops. It stops from here and return there because of this negative, a force of repulsion will be there. So it returns back to the gap. To the gap. Gap is near to the cavity. To the gap for the second time. First time it comes towards the Rippler. Next it goes back towards the gap. Now the electron A stops and returns back to the gap for the second time, and it will get absorbed by the cavity. So what happens? So that electron A, it will trace a curved path in the graph. It will trace a, write it with the red only. It will trace a curved path in the graph. It will trace a curved path in the graph. Okay. Curved path. It's not like that. It will trace a curved path. Curved path. Okay, in the graph. So that I will write here. The point what I discussed, I will write here. Okay, that's the first point. I will write in the applique diagram. As shown in the figure. A is the reference electron. A is the reference electron that passes what? Through the gap. When the gap voltage that passes through the gap, when the gap voltage is here, and it is going negative. Okay. So next point, you can see that gap Vt is going negative. Okay. So electron A is unaffected by this voltage. Unaffected by this 0 voltage. By this 0 voltage. Now what happened? Across the by this 0 voltage across the gap. Across the gap and it continues to move. It continues to move with initial velocity of v suffix naught. Okay, till it enters the reflex phase. It enters the reflex phase. Now, what happened in the reflex phase? In the reflex phase, a force of repulsion will be there. A force of repulsion acts on the electron. Why? Due to voltage on the reflex. Due to what voltage? Negative voltage. I will write that. Due to negative voltage on the reflex. Okay. Negative voltage on the reflex. What happened? Next, there will be what I told you. A force of repulsion acts on an electron A due to negative voltage on the reflex. So this electron, the electron A, penetrates to a certain depth. Penetrate to a certain depth in the reflex phase. Due to momentum. Due to its momentum. Okay. So that is shown in figure D. Figure D. I indicate that. Okay. So the electron A, then stops. It will stop its movement, then stops and return back. To the gap. Return back to the gap for the second time. And get absorbed by the cavity. So what I can write? Therefore, the electron A that will trace a curved path, curved, a curved path That is the thing that I have applied. Okay. So this is the thing that I have just discussed here. Next I will take Next I will take the reference, what you call as the electron C, that is in the yellow color. Okay. I will take the electron C. This is the electron. Okay. That passes through the gap from that is the quarter. This is the quarter. The quarter of the cycle before A, because this is coming, C is coming before A. Okay, before A, and it will encounter a maximum positive voltage, because this electron is being encountered by a maximum positive voltage, and hence maximum, it will have, because of maximum positive voltage, it will have maximum electric field EC across the gap. Okay. So that is indicated here. You can see that in the figure. That is EC, maximum electric field. So because of this maximum electric field, a force, that is nothing but acted by the electron C due to the electric field EC, will be now, this force will be now acting on the electron C, this electron C, in the same direction as the motion of the electron C, in the same direction as the motion of electron C. And what happens? It is being accelerated, motion of the electron and C, and it is accelerated. The electron C is being accelerated. So what happens? The velocity of the electron C, Vt V naught. Okay. Since the velocity has increased, what happens is momentum also increases, and because of that, the depth of penetration will be more. You can see that the depth of penetration will be more than that of electron A. You can see that the depth of penetration is more compared to that of electron A, as shown in the figure D. And the distance, you can see that the distance traveled by the electron C is more than that of electron A. Not only that, its velocity also. That's exactly. The distance traveled by the electron C is more than that of electron A, also its velocity. Hence, we can discuss that once the distance is more, then the transit time is that also we have to keep in mind. So what is that transit time? The distance traveled by electron C is more than that of electron A. That I told you. You can see that in the graph, this graph. Hence, the ratio of distance to velocity, I will write. Hence, the ratio of velocity. What is the ratio called? Transit time. Transit time. It is so adjusted that it arrives the gap. So this electron, the transit time of this electron C, arrives the gap for the second time, because it is also penetrating the certain depth. Stop here. Because of Rupla voltage, it is being returning back. Okay. Arrives to the gap in the second time at the same instant. Consider at the same instant as that of A, electron A. So what happens? The electron C and electron A will get punched. The electron C and electron A will get punched like slowly become I'll just delete this one. Slowly it will bunch with that electron. Okay, just like it will bunch with the electron. So here it is A, C. Okay, bunch with the electron. So that I will write here. I think I will write with the same color. Okay, and electron. Okay, that passes through the gap what time? Quarter of the cycle before the electron A encounter. Okay, before the electron A it is not stylus is not working. One minute. Before the electron A, right here. Sorry. Before the electron A before the electron A before the electron A encounter maximum positive voltage. Encounter maximum positive voltage. Maximum voltage and hence maximum electricity. Maximum electric field, that is EC equal to C across the gap. That is shown in figure B. Okay. So what happens? Because of that, a force will be there. A force AC will now act on electron C. Okay, in the same direction as its motion. The same direction okay, and what happens? And it is accelerated and it is accelerated. Okay, so the velocity of the electron A, the velocity of electron C will be Vc less than V0. Okay, since the velocity has increased, its momentum also increases. Momentum also increases. Okay, and because of that, the depth of penetration, will be more, and that of electronics will be more than that of electronics. Will be more than that of electron A. That is shown in figure. Okay. So the distance traveled will be, and its velocity also. Okay, the distance traveled by electron C by electron C electron C is more okay than A, than electron A, and also its hence what happens, I can told that the ratio, as I told you, hence ratio distance to velocity is called as transit ratio. Distance to velocity, which is given by transit time. So that it arrives at the gas the second time, for the second time, the same instant the same that of A, thus C and electron A bunch. Okay, this is the second case what I have discussed just now. Okay, now we can see about the third thing. Sorry, what is that? The electron P. In the similar manner, you take down this one. This one, I'll write with the greening. Okay. The electron B, just like electron P, that passes through the gap. This also quarter of a cycle. This one, quarter of a cycle. After A, this is C before A, B after A. What it will experience? It experiences a maximum negative voltage, and hence maximum negative electric field. Okay, because of that it will have maximum negative electric field. So that is shown in the figure C, maximum negative electric field, this one. Because of that it will have maximum negative electric field across the gap, that is shown in figure C. Because of that also there will be a force FB will now act on this electron B in a direction. In the previous case, that force was acting on the same direction. Here, the force FB, because of that electric field EB, will now act on the electron B in a direction opposite to its motion. That is very important. In a direction opposite to its motion, and in the previous case, it's in the same direction and it is accelerated. Here, in a direction opposite to its motion, and it is retarded. So what happens? The velocity of electron B will be Vb greater than V0. Since the velocity has decreased, the momentum also decreases. The depth of penetration will be less. You can say that the depth of penetration will be less as that of electron A, shown in figure D. Because of that, the distance travelled and the velocity of electron B are both less than that of electron A and electron C. And the distance by velocity is nothing but transit time. It gets so adjusted that this electron B arrives the gap in the second time at the same instant as that of electron A and C. Thus, these three electrons, that is A, C and B, will get bunched together. Okay, that's the thing here. Will get bunched together. So I draw that also. Slowly it will move like this and it will get bunched together. Okay, it comes in the same direction. Okay, that is B. Either it will come. Okay. Similar case is that is A, B and C. One more thing I will take. An electron which passes through the gap earlier to C. This one. This electron. Earlier to C. So that will encounter a this one, earlier to C, not this one, it is earlier to C, this one, this point, okay, I'll write that one. This one, earlier to C, that will encounter a lesser positive voltage because it has a positive voltage less than that of C, lesser positive voltage. So what happens? So the depth of penetration is less compared to that of C, but the transit time, which is nothing but distance by velocity, which is nothing but transit time, is not longer for this electron, and it comes back to the gap before the bunch, and comes back to the gap before the bunch, like okay, like this it comes. So this electron C, that is this electron called some other electron, a star, something like that, which passes through the gap. That is passes through the gap. This electron is earlier to the electron C, and it will experience a positive voltage less compared to that of electron C, and because of that, the depth of penetration is less compared to that of C, but the distance by velocity, which is nothing but transit time, is no longer for this electron, and it comes back to the gap before the bunch. Similar is the case of this also, the electron B also. Okay, not electron B, I will call this as this also a star. Okay, another electron, this electron, which passes through the gap after the electron B. So this is after electron B. That will encounter a lesser negative, you can say lesser negative, because it is going to 0. So lesser negative voltage. So the depth of penetration will be less. Sorry, depth of penetration will be more compared to that of electron B. Okay, depth of penetration will be more compared to that of electron B. Okay, that also you can. This depth of penetration will be less compared to that of electron C. This depth of penetration will be more compared to that of electron B, but less than that of electron A. Okay. Depth of penetration will be more compared to that of electron B, but the transit time, which is nothing but distance by velocity, is not shorter for this electron to join back the bunch, and it comes back to the gap after the bunch. So what happens? This will come like this, and it will come after the bunch. This electron will come after the bunch. Keep in mind. So this is nothing but bunch electron bunch. Okay, write it another. This point is nothing but electron. Okay. So the bunching limit is from, I can call it as from positive maximum to negative maximum. So this is nothing but the bunching limit. Positive maximum to negative maximum, bunching limit. Bunching limit. Okay. Positive maximum of the RF voltage. Sorry, positive maximum to negative maximum of the RF voltage, and it will occur only once in a cycle only. Okay. Therefore, the I said to you, one bunches occurs only once per cycle. That is being centered around the electron A. That is the electron is called as a reference electrode. And what happens? It will transfer the energy to the cavity to conserve the total power. This electron, bunch electron, will transfer the what you call as energy to the cavity in order to conserve the total power. And you have to keep in mind, the power delivered by the bunch electron in the cavity should always greater than the power loss in the cavity. If that is not happening, then oscillation will not occur. Okay, so the power delivered by the bunch electron should be greater than that of power loss in the cavity, and the electromagnetic field amplitude at the resonance frequency of the cavity will increases in order to produce the microwave oscillation. Okay, what I told you, the electron bunching, after the electron bunching, the total power will be delivered to the cavity. That the total power delivered to the cavity should be always greater than that of power loss in the cavity, and the electromagnetic field amplitude of the resonance frequency of the cavity will increases. That means the electromagnetic field amplitude at a resonance frequency will increases in order to produce the what you call as microwave oscillation, because of the total power delivered by the bunch electron to the cavity. What happens? The electromagnetic field amplitude increases and the microwave oscillation is being set up in the reflex klystron, and the RF power that is being produced can be taken out from the cavity, or it is being coupled to the output through a coupling loop and can be taken out from the cavity that is being indicated in the figure. Okay, so this is the mechanism of oscillation of what you call as cavity reflex klystron oscillator. Okay, so this point I will write. This is nothing but n that occurs at 2, 3 by 4 sides from here to here, and this period is nothing but okay, and from right from this reference point A to this point, I will take that n equal to 1, 3 by 4 cycles, and 3 by 4 cycles, that is important. Okay, this is 2, 3 by 4 cycles. Okay, so this is the thing that is being indicated here. So I will just this diagram, the figure A is nothing but the figure A. All this figure is called as applicate diagram. Okay, I can call the figure B. This figure B, I can call it as maximum positive across gap. Maximum positive voltage across the gap. This is nothing but maximum negative voltage across gap. And this is nothing but the depth of penetration of electron. This is nothing but depth of penetration of electron in reflex space. Depth of penetration of electron in reflex space. So these are the things. I write that that point also. That is the last section. The similar things what I have indicated in this yellow line, but only small changes is the. If I can copy this one, then good, so that is possible. It's not possible. I'll just see. Okay, I not verify that one is possible. The same thing only. This, because so that I don't want to write it again. That is why I try to do that one. Okay. Anyway, I will write once more. I will write with the screen. Okay. So next point is an electron B. What that passes through the gap quarter of a cycle electron A experience maximum negative voltage, and hence what will have maximum negative electric field, and hence maximum negative electric field, what is nothing but EB across gap shown in figure C. Okay, so that what happens, a force of because of that a force Fc will now act on electron B. Okay, electron B in a direction opposite to the OPPO SIT. Okay, opposite to its motion. And opposite, and it is retarded. Previously it is at rate and it is retarded. So the velocity of the electron B will now be Vp greater than V0. Since the velocity increases, what I told now will be V greater than, since the velocity has decreased, what is where is momentum also decreases. Is the momentum also decreases, and what happens, and the depth of penetration will be less than that of electron A, shown in figure D, and that of electron A. Okay, shown in figure D. Then what happens? The distance traveled with the velocity. The distance traveled and velocity. Okay, velocity of the electron B, the distance traveled and velocity of electron B are both less than are both less than what? Those of electron A. Those of electron A. And distance by velocity, that is the transit time. And transit time, it gets so adjusted that it arrives at the gap. It arrives at the gap in the second time. In the second time, at the same instant as those of electron C and A. Thus, the three type of electron, thus the three type of electrons of electron, which are electrons C, A and B, C, A and B. Okay, this is the thing that is happening. So next is other two octaves that will be not participate in the bungee. Okay, that was the right with the blue ring. Okay, an electron. Bring down. An electron which passes through the gap after what electron B, after electron B encounter a lesser positive voltage the depth of penetration is less, so that depth of the depth of penetration is not good. Is less compared to C. Compared to the electron C. Okay, but the transit time is not longer for this electron. It comes back and it is to the gap before the bunch. Before the before. Similar the other case also, I will write. It is taking too lengthy. Everything is being stuck. Another electron I guess it's not working properly. Another electron which is passes through the gap after electron B encounter the negative encounter a lesser negative voltage. So that the depth of penetration, so that depth of penetration is more electron B is more compared to B. But the transit time is not shorter, this electron to join the bunch. And comes back to the gap after the bunch, and comes back after the bunch. These are the things happening in the applicate diagram. Now we can do the conclusion part of this one. See, my stylus is not working, that is why it is being delayed. Okay. Now I will see the conclusion part. Thus, the bungee limit is from That's the bunching limit. Bunching is the bunching limit is from positive to negative maximum. Okay, so just my stylus is not working. Okay, so just manage with this one. Okay, maximum of the RF voltage cycle only. Okay. Therefore, the bunch bunches occurs only one cycle centered around